In this video, we focus on capacitors. We will describe what a capacitor is and its main characteristics, its capacitance. We will focus on parallel plate capacitors. Then we will look at capacitors as a way of storing electrical energy, and we will calculate how much energy is stored in a parallel plate capacitor. I will expand this idea to a general electric field and see that the building of an electric field is in itself a way of storing energy. Then we will end up this video by examining what is the equivalent capacity of a combination of capacitors. So we will begin by remembering that we saw in the previous video that for any conductor there was a relationship between the charge it had and the electric potential it had. Q divided by V was a constant that depended on the characteristics of the conductor, and this is called the self-capacitance. Then we can describe a capacitor as a device that consists on two conductors that have the same charge with opposite signs. This is one with plus Q and the other one with a charge of minus Q. For the capacitors, we can show that there is a direct relationship between the amount of charge stored in the capacitor and the difference of electric potential between both conductors. And this capacitance, which we define as the ratio between the charge and the potential difference, is a constant that only depends on the shape, size, and geometrical characteristics of the capacitor, but not on its charge, nor on its difference of potential. We can draw an analogy with the idea of the speed of propagating waves in a medium. If you remember, the speed did depend only on the characteristics of the medium. However, it established a relationship between the frequency and the wave number, but it did not depend neither on the frequency nor on the wave number. So this is the same idea. Even though the capacitance of a capacitor establishes a relationship between the charge that the capacitor is storing and the potential difference between both conductors, the capacitance does not depend on neither of them, but on the characteristics of the capacitor, mainly on its geometry. The unit in this international system for measuring the capacitance of a capacitor is the farad. And 1 farad is 1 coulomb divided by 1 volt. However, this magnitude is quite big, so normally you can measure the capacitance of normal capacitors between microfarads and picofarads. We will begin by deriving what the capacitance of a parallel plate capacitor is. So a parallel capacitor is one of the most common capacitors used, and it's built by two parallel plane conductors, one with charge plus Q and the other with charge minus Q. I'm going to go to a sort of blackboard to explain myself with more details than in the slides. So, as I said, we're going to begin with the capacitance. And in particular, we will focus on the parallel plate capacitor. So for this capacitor, I was telling you that you had two plates. That's the one on top. This is the one on the bottom side. And then the geometry of the capacitor is, we're going to characterize this capacitor because the plates have an area of A and they are located at a distance B. Even though this is the drawing, normally these quite smaller than any of the sides of the parallel plate. So we're going to work here in infinite plane approximation. Okay, so our objective is to derive what the capacitance of this parallel plate capacitor is. We're going to denote the capacitance by C. And this we know it's the relationship between the total charge in the capacitor and the potential difference. So if we think that the upper plate is charged with charge plus Q and the lower plate with charge minus Q, we can say that this is point A, this is point B. So the electric potential at A is going to be bigger than at B, and this is what we call directly V. Okay, the V that you have in the definition of the capacitance. So we want to know we want to relate both, and the way to relate them is going to be using the electric field, because we can establish a relationship between the charge of the plates and the electrical field between the plates, and we can also establish a relationship between the potential difference between the plates and the electrical field. So let's start by the first one. We know we know what in the approximation of infinite plane, we know what the electric field of an infinite plane of charge sigma is. So if you remember, we call sigma to the surface density charge. And in this case, we could calculate it as the total Q divided by the area, okay? So if we get infinite plane, a charge with surface density charge sigma, we know that it's, and this is positive, we know that it establishes across space an electrical field that is parallel, and it's going out of the plane, and the electrical field is constant and is just sigma divided by 2 epsilon sub 0. If you don't remember, you just have to use Gauss's law. You put a surface that is a cylinder, and then you call S to this part, and then the total electric flux through the surface is going to be S times E, and this has to be equal to the amount of charge that is intersected here, which is S times sigma divided by epsilon sub 0. And here I forgot to put a 2 because you have 2 plates here, two areas. Okay, so with this you can come to this conclusion. Okay, so now we don't have only one plane, but we have 2 planes, one positively charged and the other negatively charged. So what we're going to have is the electric field with this positively charged and this negatively charged is going to be double here, okay, because you will have from this positively charged a field that is going to be sigma divided by 2 epsilon sub 0, and from this negative one you're going to have also another one that is going to be sigma divided by 2 epsilon sub 0. So the total electric field here is going to be sigma divided by epsilon sub 0, okay? And outside, both electric fields are going to cancel out. So I'm going to have here the electric field is going to be 0, and the electric field outside is going to be 0. Okay, so this capacitor is managing to store all the electrical field between the plates of the conductor. Okay, so now we know there is a relationship between the electrical field and the total charge, because we know the electrical field is sigma divided by epsilon sub 0, which is Q divided by A epsilon sub 0, okay, because we've used this expression here. Okay, so this is our first connection here, and now we're going to focus on how the potential difference between plates is going to relate to the electrical field. And for that, we have to bring back our knowledge. If this is point A and this is point B, we know that VA minus VB, which is directly what we are calling the potential difference, is going to be minus integral from B to A of the electrical field differential of path. So we're going to take a path that just goes from one to the other, parallel to the electrical field. And as the electrical field is constant, it does not depend on the path. This is going to be equal to plus the integral from A to B of the electrical field differential of path. Here they're both parallel, so this is positive, and E, they're both parallel and it's positive, so this is just E times the distance between both plates that we call at the beginning D. Okay, so now we know that V is equal to E times D. So the thing we have to derive now is the capacitance, if you remember. This has to be Q divided by V. This is Q divided by E times D, and we already know that E is Q divided by epsilon sub 0 A times D. So the capacitance of this parallel plate capacitor is epsilon sub 0 times A divided by D, where A is the area of the plates, D is the distance between them, and epsilon sub 0 is the electric constant. Okay, so this is only valid for a parallel plate capacitor. However, different capacitors will also have an expression that will depend on the geometry, on the characteristics. We could have derived another expression for the cylindrical capacitor, which is built up by two cylinders, one with charge plus Q and the other one with charge minus Q. That could also be a capacitor, and it's going to have a capacitance that's going to depend on the geometry, and it's not going to be the same as the parallel plate one. Here, at this point, I suggest you go back to problem 7 and you look at it as a capacitor, because in problem 7 you have two concentrical conducting spherical shells, one with charge plus Q and the other one with charge minus Q. So in itself, it's also another example of capacitor. Okay, so once we know this, the capacitance of a parallel plate capacitor, I'm going to go to the second point I wanted to cover, which is the storage of electrical energy. Okay, so for this derivation, I'm going to use also the idea of the parallel capacitor. Okay, in a parallel capacitor, if we want to charge a parallel capacitor, we can begin by having a charge initially. So initially it's on charge, and then we might have at some time t, might have some charge on it, and then at the end we might have a whole charge. We're going to denote that by big Q. So there's going to be a difference of potential. Let's call it VA minus VB, where this is A, this is B. And at the beginning it's going to be 0, then at a certain point it's going to be V, and at the end it's going to be a very big B. Okay? So the idea, if you remember, of the energy we store, whenever we want to charge this parallel plate capacitor, we have to, if this is going to be the plus area and this is going to be the minus plate, what we have to do is imagine the charges are positive, which is a bit easier for our derivation. So when we want to charge the capacitor, we have to take some charge from this plate and put it into the other plate. Okay, so imagine we've been doing that for some time, and we are at this moment when the charge of the capacitor is Q and the potential difference is V. So we want to charge it a bit more, so we take dQ and we move it to the upper plane, and then we are storing a bit more of energy, which is given by du, and this is equal to the work we have to do against the field to charge it, which is, if you remember and if you've done the exercises, it's the amount of charge times the potential difference, so the end point minus the beginning point. So this is going to be just V times dq. Okay, so we know that du is V dq, and we also know that the capacitance, which is the ratio between the charge and the potential difference, is valid for the capacitor with any charge. So it is valid when it's totally charged, and it's valid when it's halfway charged. So we can use this and say that here V has to be Q divided by C. So here we have Q divided by C ddq. Okay, so now to calculate the whole energy store, we just have to integrate from 0 to the whole energy, and here from 0 to the whole charge. Okay, so this integral here from 0 to big Q, so this integral is just equal to U, and this part of the integral is 1 divided by C, integral from 0 to big Q of Q dq. And if you integrate this, this provides square Q divided by 2 between 0 and Q. This is the total energy is equal to 1 over 2 square Q divided by C. Okay, you can also use this expression. Okay, and this then is equal to 1 over 2 of Q times V, and it's also equal to 1 over 2 C square V. Any of these, all of them are equivalent. Okay. Okay, so now I want to make a small point, thinking that at the same time we've managed to charge the capacitor, we've managed to establish an electrical field between the plates. Okay, I'm here drawing it. You know that the electrical field between the plates is going to be, because we've already calculated, the electrical field is related to the differential of potential. So big V is going to be equal to the electric field we've managed to develop there times the distance between the plates. We also know that the total energy stored there is 1 over 2 C times square V. And we also know that for this parallel plate capacitor, its capacitance is equal to the area times epsilon sub 0 divided by D. Okay, so I'm going to look at this at the same storage of energy from the point of view of building up an electrical field. Okay, so the storage of energy, which is 1 over 2 times C. C here is A times epsilon sub 0 divided by D, times V, which is E D, and this is squared. Okay, I'm just putting this equation here, changing V by this one and changing C by this one. Okay, so this is equal to 1 over 2 epsilon sub 0 square E, the electric field, times A times D. Okay, now I want you to focus on this term here. Okay, and if you notice, this term is the product of the area between the parallel plate capacitors, okay, and the distance. So it's giving you the volume, actually. So this is the volume, okay, the volume where the electric field is established. Because remember that for this parallel plate capacitor, the electric field outside the plates is 0. So all the electric field is established between the plates. So in fact, this is U is giving you with this U we can look for an energy density of an electrostatic field. So I'm going to call that small u and with an E, and that's going to be the energy density of an electrostatic field. And I'm going to define it as the whole energy divided by the volume where it is stored. So this, if I divide by the volume, is 1 over 2 epsilon sub 0 square electric field. So we can also see that building up an electric field is also a way of storing energy. And even though we've derived this for the parallel plate capacitor, this expression here is valid for any for the establishment of any electrical field. Okay, the last part I wanted to cover in this video is the combination of capacitors. Okay, so here what we want to do is to find what is the equivalent capacity of a combination of capacitors. So capacitors and other devices, electric devices, can be mainly connected in what we call parallel or in series. So what is connecting capacitors in parallel? Well, imagine I have two capacitors, which I plot here. This is the plate, the positive plate, and this is the negative plate of one of them, and here is the positive plate and the negative plate of the other. Okay, so there I have two capacitors, and then I'm going to connect them in parallel. Okay, so in parallel they are connected by wires in this way. Okay, so the blue represents the wires. I'm going to call this point A, and this is going to be point B. Okay, so VA minus VB is equal to the potential difference. And these wires are conductors. So once the electrostatic equilibrium is established, the electric potential in any part of this wire is the same. So VA is the same here than here. Okay, so the potential, the electric potential on this plate, the upper plate, is VA here and also here. And on the other hand, in the lower part, we have VB here, and it's the same potential as in the lower plates of the both capacitors. Okay, so the first capacitor I'm going to call number 1, and I'm going to say that it has a charge plus Q and a charge minus Q1, and the second one labeled with number 2, and it has plus Q2 and minus Q2. Okay, and in principle this has capacitance C1 and the second one has capacitance C2. So if I call V1 to the difference of potential between the plates of the first capacitor, and V2 the difference of potential between the plates of the second capacitor, I can say that C1 has to be Q1 divided by V1, while C2 has to be Q2 divided by V2. Okay. However, as I was saying, V1 has to be equal to the difference, the potential difference between both plates of the first capacitor, which are exactly the difference of potential between VA and VB. This is exactly what we're calling V. And the same, we can just derive the same for the second capacitor. So both have a difference of potential given by V. Okay, so this is connecting them in parallel, and what we want to know is what would be the equivalent capacity. Okay, so we want to transform this into a different capacitor. Okay, I'm going to draw it. So this has to be equivalent to just one capacitor. Okay, that is storing the same charge at the same potential difference. This has to be A, this has to be B. Again, V is going to be VA minus VB. And here in the positive plate, I'm going to charge it with plus Q, and in the negative plate with minus Q. And it has to be equivalent. So in the upper plot, I'm charging, the whole charge is given by the charge of the first one plus the charge of the second one. So Q, in this case, has to be equal to Q1 plus Q2. Okay. In the equivalent capacity, this capacitor, the equivalent one, we're going to say that it has the capacitance, the equivalent capacitance. And as it is a new capacitor, this equivalent capacitance has to be equal to the total charge stored divided by the difference of potential. Okay, so now we bring everything together and we say, okay, if Q is equal to Q1 plus Q2, and I take from here that Q1 is equal to C1 V1, and from here that Q2 is equal to C2 V2, then we can come to the conclusion that this has to be C1 plus, times V1 plus C2 times V2. And this has to be equal to the equivalent capacitance times V. So from here, as V1 and V2 are equal to V, we say that C the equivalent capacitance times V has to be equal to C1 plus C2 times V. This is the equivalent capacitance of a combination of two capacitors laid out in a parallel fashion has to be the addition of the capacitance of the first plus the capacitance of the second. Okay, so this is if you only have two. If you have several, I don't know, 3, 4, any, and they're all combined in parallel, this is the first one, and this is the second one, and the third one, and as many as you want, okay, and they're all combined in parallel in this fashion. So this is the first one, the second one, third one, up to n. Then the equivalent capacity of all of them is the addition from 1 to n of the individual capacitance. Okay, so this is for combining them in parallel. So now we're going to derive the same idea, or the same equivalent capacitance for a different combination, which is in series. Okay. So what is to combine capacitors in series? Well, capacitors combined in series look like this. So this is the first capacitor, and this is the second one, okay? And they are combined in series, which means that the positive plate of the first one, which is up here, this is the negative plate of the second one. We're going to combine the positive plate of the second one with the negative plate of the, oops, sorry, I don't know what I did here. Okay, there we are. With the negative plate of the one up there. So this has to be point A, this has to be point B, okay? This is C1, this is C2. The difference of potential between plates of the first one is V1, between plates of the second one is V2, so C1 has to be Q1 divided by V1, and C2 has to be equal to Q2 divided by V2, okay? So here we have to realize two things. One of them is that this is a wire, so everything here has the same potential, so the potential here is A. Here we're going to call this point C, and the electric potential at point C is the same as at this point, okay, because it's connected by a wire, and this point is connected to point B. So here we have difference of potential. We have potential, the same potential as in point B, okay. So what I want to come up with is that VA minus VC is equal to V1, VC minus VB is equal to V2, okay? So if we add up these two, we come up with VA minus VB equal to V1 plus V2, okay? This is one of the things I wanted you to notice. And the other one I want to notice is that this capacitors connected in series, they begin by being neutral, and then they begin charging, okay? They charge together. So any positive charge, that is any electron that comes from this plate here and goes to the other plate, the charge of the first one and the second one are not independent, okay? So they begin charging at the same time, so the electrons, the surplus of electrons in this plate here is equal to the deficit of electrons in this plate here. This is the total charge I'm having here is Q, and it's the same as Q1 and the same as Q2, okay? So with these two ideas, I want to build equivalent capacitor, which is only going to be one. Okay, I'm plotting it here. This is the equivalent capacitor. And this here is point A, and this here is point B, okay? And this equivalent capacitor has a capacitance of C equivalent, and then this is charged with plus Q, and it's in the upper plate and with charge minus Q in the lower plate, which is exactly Q1 and exactly Q2. Okay, so here to derive, and the last thing is that the equivalent capacitance has to be equal to Q divided by V, where V is VA minus VB. Okay, so here to derive the equivalent capacity, we begin by seeing that V is equal to V1 plus V2. This is that here V is equal to Q divided by C equivalent. This is Q divided by C equivalent has to be V1. V1 is charge 1 divided by C1, and V2 is equal to charge 2 divided by C2. This is equal to Q1 divided by C1 plus Q2 divided by C2. As we've argued before, Q1 and Q2 are the same, so Q divided by the equivalent capacitance has to be equal to Q divided by C1 plus Q divided by C2. This is that 1 divided by the equivalent capacity has to be 1 divided by C1 plus 1 divided by C2. This is the equivalent capacity has to be the inverse of the addition of the different capacitance to the minus 1. So in this case, we put in just 1 up to 2, but if you had a set of n capacitors connected in series, the equivalent capacity would be equal to the addition of 1 over each capacitance, all the inverse of that. Okay, so and what would it look like? Well, it would look like this is C1, this is C2, this is C3, etc. up to Cn. Okay, C1, C2, C3, etc. Cn, and they're all connected in series. Okay. Okay, and their equivalent capacity would be given by this. Okay, so before stopping this video, I wanted just to mention the problems you can try to accomplish right now, which would be you could take a look again at number 7 and see that this number 7 is in reality a capacitor, because it's built up with 2 conducting concentrical spherical shells that have the same magnitude but opposite sign, which is a capacitor. Then you could do problem 8, and you could also solve problem 11. So thank you for attention. I hope it was useful.